To our past alumni, our guests. Really appreciate you guys being here. So today we have Marco Carmosino. Forgive me if I'm mispronouncing that. Who's joining us today to talk to us about algorithms. So we're going to pass it on off to Marco, and Marco, you're up.
All right. Hi, everybody. And thank you for coming to my Algorithms for Boot Campers talk. I really like giving this talk, and any feedback or questions you have would be very much appreciated. So a little bit on my background. I finished a PhD at UCSD in computer science last year in August. And now I'm at the Pacific Institute for Mathematical Sciences at Simon Fraser University in Canada. And I work on theoretical aspects of algorithm design and machine learning and computational complexity theory. So I think it's important to be able to explain that stuff to actual professional programmers, you guys. So let's get started. What even is an algorithm? So I like to look up things in the dictionary when I do not know what they are. Webster claims that an algorithm is a step-by-step procedure for solving a problem or accomplishing some end, especially by a computer. And that's not the most helpful definition in the world, because this could mean a lot of different things, right? So, for instance, I have lots of problems. I have the flu. Maybe I lose my phone. Maybe I have a sandwich that doesn't taste so good. You know, these are not problems that algorithms can help you with. I'm sorry. Instead, when we want to talk about algorithms, we want to talk about the types of problems that are appropriately targeted with computational solutions. So what does that mean? That means that we need to be able to precisely specify a set of inputs, a rule, and then a set of outputs for our problem, okay? So for example, let me give some examples of inputs and outputs, precise specifications of inputs and outputs. Arrays of numbers, strings, single numbers. For outputs, you could have, again, single numbers, strings, arrays of numbers. And these should feel super familiar because they're the types available to you in your favorite programming languages of Ruby or JavaScript. Also Booleans. And the rule should have the property that for each input, there's one and only one output, okay? So that's a problem. It's this very precise setup where we have this precise world of inputs, precise world of outputs. You can think of them as your favorite types from your favorite programming language. And each input goes to one and only one output. Let's give some examples of problems now that we know what the setup is like. These are going to be very simple. We could take an array of numbers and we could give the sum of that array, right? That's mapping an array to a single number. We could take a string and we could ask for the length of that string. It's the length problem. That's mapping a string of characters to a single number. We could take two numbers and we could ask for an array that gives you every number between those numbers, right? So that's mapping two numbers over to an array. These are very simple problems, but the reason that I'm using them as an example is because they clearly say, okay, there's this very precise input domain, this precise output domain, and a clear rule that takes inputs to outputs. Okay, so that's what a problem is. You know, we've got our highlighted word from Webster's definition. Now, what's an algorithm? Remember, here's our setup. A rule doesn't tell you how to associate inputs with outputs, right? It just tells you what. A rule is what you want, not how to do it. If I tell you to sum up an array, you can easily imagine, okay, I write a loop that adds together the first element, the second element, so on and so forth. But that's not the rule itself. That's how you do the rule. An algorithm is the precise specification of steps that actually execute the rule. The rule is the what, the algorithm is the how. Okay? So again, let's flash Webster in front of our faces. A step-by-step procedure for solving a problem. And let's get that picture up again. The algorithm is between the inputs and the outputs. It is a precise set of steps that actually implements the problem rule. It's the how to the rule's what. And when I say precise, that doesn't necessarily mean code. That doesn't necessarily mean software, right? As long as you describe the inputs, the outputs, the rule, and the algorithm itself precisely, you could do that. You could do that in Ruby. You could do that in pseudocode, which I'm sure many of you have seen. You could do that in natural language. You could do that in English if you're careful enough to specify exactly what you mean with each step. You could also do it with mathematics or even a diagram, right? Algorithms transcend programming languages. They're the precise specification of steps themselves, not necessarily the code that executes that specification. So let's recap quickly what algorithms actually are. Our problem is inputs, outputs, and a precise rule, the what, mapping inputs to outputs. And our algorithm is the precise steps that implement that rule. Okay, a recipe for turning inputs into outputs. At this point, I'll pause for questions. I don't super know how that works on Zoom because I haven't done one of these talks yet, but.
I'd say if anyone has a question, either pipe up or you can put it in the chat and I can always pass it off to Marco.
Yeah, I guess drop questions into chat. And if I see questions pop up into chat or they get surfaced to me from Kate, I'll get to them, okay? All right, so let's move on. Now that we know what algorithms are, why study them? Why know anything about algorithms? So first off, my motivation for thinking about algorithms is understanding. Our world is rife with algorithms. They run the programming environments that we use. They run our financial institutions, our healthcare system. Our world is lousy with algorithms, and it's good to understand those things. Second, flexibility. So I imagine you all know what CRUD is because you've been studying at a solid web development bootcamp. And CRUD is a general paradigm for building applications, right? Like it has designs that it does well with, and then it has designs where it does not do so well. Sometimes you need to write computer programs that break out of the CRUD paradigm. That is when that's when knowing algorithms becomes useful because you can design programs that sort of get you outside of the CRUD envelope. And then finally, cash money. Some jobs and some problems require an understanding of algorithms, either because they have problems that aren't amenable to CRUD solutions, or because they have problems at such a scale that you really need to pay attention to efficiency and you can't use like a normal database to solve those problems, okay? So this is why we might want to actually learn about algorithms. Curiosity, flexibility, and many dollars. Okay, so for the remainder of the talk, I'm going to lay out, when do you need an algorithm? How can you tell that you actually need an algorithm? Once you know you need one, how do you apply that? And then I'm going to tell some fun stories about applying algorithms to problems in the world. So when do algorithms actually apply? So maybe you're trying to write a CRUD program for your solution and you notice that it's not flexible enough. That's your first test. Check yourself. Am I outside the CRUD paradigm? Okay. Next step. Do you actually need to define a problem like one of those precise IO problems? Maybe not. Instead, just write down roughly what you want to do. Google for gems that do that thing. Stop if you find one. You don't need an algorithm. Just look for gems. If you don't find one, more precisely write down that input-output task and Google for gems again. If this process fails, if you don't find a gem to handle your job for you, then you might actually need an algorithm. You might need a customized solution. So now you need to ask yourself, can you even define one of these precise problems for the situation you're in? Here's some examples of input-output domains that aren't so simple. They're not just types in your programming language, like our previous ones. Maybe you have some kind of scheduling requirement for a college. You're trying to assign rooms to courses or something. Maybe you have a bunch of sensor data and some scientists want you to do something with it. You're not sure. You want to turn it into an industrial process control or something. This is the hard part of figuring out if algorithms even apply or if you can use them. It's turning these messy real-world situations into a precise problem specification, input domain, output domain, and a rule that associates them. So the way that I like to think of this process is as a modeling process. Your inputs are a model of the real world, and your outputs are also a model of the real world. They're what you want to see. I'll get back to that in a second. And then finally, once you've actually got a problem, then you can start checking the algorithms textbooks. Then you can say, okay, is there an algorithm out there that can efficiently solve my problem that I can actually implement? So let's recap that step by step. First, check if you can use CRUD to solve your problem. If you can, there's no reason to not let the database do the work for you. And databases are wonderful things these days. Like Postgres has amazing algorithmic capabilities. That's really what it is. It's a whole bunch of algorithms prearranged for you and baked together such that you can use it with SQL instead of cooking up your own algorithmic solutions. If you can't use CRUD, then okay, continue. Check for gems. If somebody else has already written code that solves your problem, just use that. It will make your life easier and you will be happier. If there's no gems to solve your problem, well, then you're stuck writing down that precise input-output rule model. And if you can convince yourself that you can accurately model your situation, then congratulations, you might actually be able to use an algorithm if there's an efficient algorithm for your problem. Again, it all hinges on this process of defining a problem, which is fundamentally a modeling question, a translation question. It's all about finding the right model. You're taking a complex real-world situation and transforming it into a simplified representation that still reflects the key aspects of the problem and gets your work done. And if you know how to write down these models of the real world, you can use algorithms. You will know how to recognize the situations where algorithms are actually useful. And there's not really a way to teach this except through examples and practice. It's just like learning to translate, say, English to Spanish or vice versa. You need to find a good translation of your real problem into this precise formal language and then try and throw an algorithm at it. So what we're going to talk about for the rest of the talk is just some examples, and then I'm going to give you resources where you can start getting exposure to these modeling techniques and deploying algorithms. Okay, so roughly, modeling tools live in books, and they live in two different kinds of books. The first kind, which has gotten a lot of press recently, is statistical models, also known as machine learning. The other kind, which has gotten a lot less press, even though it should, because they're more common and more successful, arguably, is combinatorial models. So a combinatorial model is a situation where there's no noise in the input, there's no uncertainty, there's no weird missing values, and the input is very well described by some discrete data structures, by which I mean arrays, so collections of documents or strings, a dictionary like a hash file, or a graph, which we'll get to graphs in a minute because they are some of the most fundamental combinatorial models, and they're used everywhere. A statistical model, on the other hand, is what you use when your input is noisy or uncertain. It's when your input is a bunch of observations of some kind of population, like surveys or polls or user profiles. Anytime you're collecting data, you probably want to use a statistical model. Any examples of a pattern, like spam or not spam, converted users versus unconverted users, users that bought your product or not, or users and product reviews. Maybe you can predict how much a user is going to like a certain product based on their profile. Netflix does this all the time. These are statistical models of user behavior, and they rely on algorithms. This type of algorithmic task is associated with many buzzwords that have become very popular in the media. So if you hear buzzwords like machine learning, AI, or deep learning, or knowledge discovery, probably you're dealing with a statistical model. Okay, so let's go into some examples of when algorithms are useful. And we're going to do that by just a few examples of modeling things, just to get a feel for what that process is like. And I'm going to throw a model in your face. I'm not even going to tell you what it's about, but you're going to be able to tell me what this is. Like, what is this a model of?
Airports.
Yeah, it's airports. This is airports and flights between them. And you didn't have to know anything from an algorithms class to know that. So this structure that I've put in front of you is a type of model called a graph. And right now it's modeling the flight network. Let's break down the anatomy of how you model stuff with a graph. There's things called nodes, which we use to represent cities on the other page. There's things called edges, which we use to represent flights. Edges connect the nodes. Edges could have a direction, right? Like maybe there's only a one-way flight from one place to another. Or edges could be in both directions. Nodes can have labels. So we labeled our cities with their airport codes on the last page. And edges can also have labels. Edges can be labeled with numbers, where the edges are sometimes called weights, or they could be labeled with strings. Okay, so a sensible label for our edges on the other screen could have been cost. Like, how many dollars does it take to catch a flight from one city to another? Yeah, we could also call edges with strings, but that's not going to be super useful for this example. Okay, so now that we've got this model of the real world, we can think about the types of properties that we can have of a graph. A graph could be undirected, and that means that edges all go both ways. There's no inherent direction. So like every road is a two-way road. That's an undirected graph. Graphs could be directed, where maybe some streets are one-way streets. So you can't go, can you see my mouse pointer? Yeah, so you have to go from this node over here to this node over here, but you can't go back. So that could model a one-way street in a city like Boston, which has many terrible one-way streets. A graph could be connected. So in this graph, I can get from this node to every other node. I can get from every node to every other node. In this graph, I can't. There's no way to get from this chunk of the graph to this chunk of the graph, okay? These are basic properties of graphs that you can use to model real-world situations. Here's some more. This is sort of a generalization of connectivity. This is reachability, where you have distinguished nodes, S and T, source and target, that you're interested in going between. And in this graph, you can't get from the source to the target. In this graph, you can. So the source can reach the target in this graph. This graph is bipartite. So this means that there's two collections of nodes. There's the green nodes and the blue nodes. And notice that there's no edges between the blue nodes and between the green nodes. Edges only go between these two different sets of nodes. And this is a not bipartite graph because there's no way to carve it up into two sets of nodes that edges only go between. Here's just one more, I promise, graph property before we actually do something with this. Distance. So you can think of the minimum distance between two nodes in a graph as the cost of getting from one node to another. So in the graph that I've splashed up over here, we can get from the source to the target in two ways, right? We could take this edge and then this edge, or we could take this edge and then this edge. If we do this path on top and we pay for each edge as we cross it, think of them as being like toll roads, we would pay 6 to get from S to T. If we take these roads, however, we would pay 5. So that means that the minimum distance between S and T in this graph is 5, not 6, because there's a good path, a cheaper path of 5. Okay, so now let's do a little bit of modeling with graphs. Whenever we're modeling a problem, we start with asking ourselves, what do we want? What do I want? What are the nodes in the graph going to represent? What are the edges going to represent? And what graph property, so of our little library of graph properties that we showed on the previous pages, what graph property do I need that maps to what I want? So let's say I want the cheapest possible ticket to Boston, right? Then nodes are going to be airports in my graph. Edges are going to be flights, and they're going to be weighted with flight prices. And then the graph property that I want is the minimum distance, right? If I only care how cheap the flight is, and I don't care at all about like number of layovers or like misery of the seat or what have you. So for this super reductive, simple situation, we've just modeled a problem with a graph. And this seems simplistic, but there were a whole bunch of companies that made a whole lot of money by solving this problem with calculations on graphs. Turns out a bunch of those companies are gone now because Google bought them. So this type of routing problem, looking at locations in the world, identifying cities with nodes and edges with roads or flights or whatever, this is ubiquitous. This type of problem is solved all the time by Amazon, UPS, Hipmunk, not Hipmunk anymore, Google Flights. You get the idea. So this is one of the many successful models of the real world that we attempt to solve with algorithms. Okay. So that was our first algorithm story of sort of like routing transit of some kind between cities by computing graph properties. Let's do another one. So once upon a time, there's a web development bootcamp. And this bootcamp, it guarantees industry internships to everybody who graduates from it. So it teaches things like HTML5 and Ruby and JavaScript. And there's a problem. You know, the boot campers learned a program, the school is popular, this is great, but somebody, let's call them Brian for lack of a better name, let's invent a fictional character. Someone has to match up these interns with their internships, and all they have to use is a spreadsheet. And that's pretty rough because, you know, there's a lot of interns, a lot of internships as the boot camp gets more popular. So can we solve this problem with an algorithm? What are we going to start with? Let's start with our input, right? Because remember, we need a very precise specified input, and then we need a rule. So the input is going to be a list of the boot campers, right? A list of the possible internships, and then some kind of preferences, right? We need to figure out a way to model the relationship between boot campers and internships. So what I'm going to propose for this example is shortlists. So for each internship, each company is going to be allowed to say, okay, of the boot campers that I interviewed, I'm going to put down 3. And those boot campers, I would be happy to come do my internship. And on the other side, for the boot campers, the same thing. For each internship that I interviewed, out of all the internships that I interviewed for, I'm going to put down 3, and I would be cool with going to do those internships. Now, what's the output going to be? It's going to be a list of pairs, right? Because you need to put boot campers at internships. And not just any pairs, we could just, you know, if it was any pairs, here's a really good algorithm. If we would accept any pairs, sort the list of boot campers alphabetically, sort the list of companies alphabetically, pair them up, problem solved. Very nice. No, we have to rule that out. So what we say is that the pairs have to respect the short list. We don't match boot campers with internships where both sides didn't agree. No, this is a good match. This is okay. Okay? And you can't put more than one boot camper in each internship, right? There's only so many slots for interns at a company. Good. And finally, we want as many boot campers as possible to get an internship. So that way we don't say, okay, we did an assignment. It's just this one. Only one person gets an internship. So we really need all 3 of these conditions to model the problem precisely. So what could you do? You know, staring at this problem, what kind of model would you go for? You can try. I'll give like a minute or so to drop some suggestions into chat. Yeah, Austin said bipartite. And Austin is exactly right. Remember the bipartite graph from earlier? Yeah, this is exactly the situation. We have 2 types of entities here. Yet students aren't going to do internships with other students. That would not work out well in the long run. So to build on that suggestion, here's the internship model. We've got one set of nodes, they're the boot campers. One set of nodes, they're the available internship slots. So if a company has 2 internships, they can stick 2 internship nodes on that side of the graph. And then the edges are going to only be drawn when both the boot camper and the company says, yeah, we could work together. Okay? So these edges only appear in the graph when both the boot camper and the internship have agreed, yeah, it's a good idea to take this internship together. And now, what I definitely didn't tell you, I told you what the shape of this graph could be, but I didn't tell you which graph property we were going to have to use. Yeah, boot camper 2 is eligible. Boot camper 1 is eligible for 2 internships. Exactly. But we need to pick one, right? So we need to know. So we need to pick some of these edges. And the graph property that we're going to use is called a maximum matching, which takes boot campers and internships and highlights certain edges. And the property that it's going to have is the following. It's a collection of edges such that at most one edge in the matching touches each node. Okay? So that's what gives you the 1 internship per boot camper rule. And then a maximum matching has the set be as big as possible given the constraints. So if we're looking at this diagram right here, this sure is a matching, right? It doesn't assign anybody twice, but it's not the one that we would want because this matching is better. It assigns more internships. Okay, so this is a resolution to our problem. We Google maximum bipartite matching Ruby, find some gem that does that. I think there actually is one. And you banish the spreadsheet for a slick Rails app. Good job, everybody. Not so much. You should not use this algorithm in production. We threw away a bunch of information. When I phrased that problem, my phrasing was kind of like cheating, right? Because I said the rankings, they're not rankings. They're just, I'll work with you or I won't work with you at all. Really, people have preferences. We should let the companies and the boot campers say, okay, this is my top choice, second choice, third choice, and then go from there. And there's an algorithm for that. It's called the stable marriage problem. And there's a whole world of variants of the stable marriage problem that you could actually figure out how to deploy in this situation. And they actually use it for matching doctors with residencies in hospitals. Look up the doctor matching market sometime. It's really a delightful example of another success of algorithms with combinatorial models, these graphs, in the real world. So even though you shouldn't use just plain old maximum matching, I hope that this story gets across another way that graphs can be successful at modeling problems in the real world for you. And here is just a big old table of many, many ways to model things with graphs. You can model transportation networks. We did that. You can model the internet. You can model games where like each node is a board position and an edge coming out of that node is a legal move to a different board position. Social networks are graphs. Financial markets are graphs. Computer circuits, actually graphs. Graph algorithms are used to decide how to lay out the chips that actually run your computers. Graphs are ubiquitous in our world, and learning about translating your problems into the languages of graphs is at least an enlightening and maybe even a rewarding skill. So let's do another algorithms story. Once upon a time, there's a beer review website because it's San Diego, and users post reviews of beer. And there's a problem though. You know, users write a lot of reviews, the site's selling ads, we're doing pretty well, but we launched without a tagging feature, right? Because we launched an MVP and we didn't think tagging was that important. It's a beer review website. And we want a tagging feature now, but we don't want tags to be a total ghost town, right? We want the users to actually use them. We don't want them to feel like nobody tags anything, because then they're not going to use the feature. Everybody's going to be sad. Okay, so again, let's try and solve this problem with an algorithm. Let's figure out the problem. Let's specify, again, our input, our rule, and our output. Input, pretty clear. It's everything that we can hoover up out of the website, right? A list of our beer reviews, those are strings. A list of the beers, also strings, and some kind of relationship to the beer reviews, so we know which beer each blob of text is about. Maybe we've got some user profile information. We've got our list of users and some click behavior. All right. And so that's our output. And we feel pretty good about our output because our output is, our input. Our input is basically whatever we've got in our database. We can write that down precisely with data structures. Our output, however, is for each beer review, we want a list of 10 words, say, we want to try and make 10 tags for each review that tag it well. Oh no, this is not a precise statement of an output, right? Like, good tags isn't precise. How do you define that? Do you say, oh, I'll know the good tags when I see them? What do you even shoot for? This is a sign that we need a statistical model instead of a combinatorial model. When you have a big pile of data and you want to make predictions that are good according to some kind of vague rule, you're in statistics land. So let's work our way through this example and see what happens. And again, the conflict here really is, what's the model? What problem do I solve? Because I don't know how to say, do a good job tagging. So let's explore that. The first thing to do in these situations is to try the dumbest model that could possibly work to represent your data. So we're going to take our beer reviews that our users slaved over. They tasted a lot of beers. They wrote a lot of words. Those words matter to them. And we are going to crush them down into what's called a bag of words, which is the dumbest representation of text you could possibly imagine. This is a bag of words. We take a description of an AI journal or a beer review on one side, and instead of caring about the order of the words or the part of speech of the words or anything like that, we just say, okay, we're going to turn it into an array. And that array is going to have one location for each word. And in that location is going to be the number of times the word was in the document. Bag of words. A document, so a review, is just how many times the word showed up in that review. This is our model. This is the foundation of how we're going to try and get good tags. And the way we're going to try and get good tags out of this is a technique called TF-IDF. That stands for term frequency inverse document frequency. This is the most mathy slide in the whole talk, so please bear with me. I am so sorry. A term frequency is just how many times does the word W show up in the document D? And if we've got bags of words, we just look that up, right? That's just the ith word in the vector. So we know that, say, hoppy corresponds to position 75. So to get the term frequency of hoppy for a particular document, we look up the 75th entry. The inverse document frequency is this fraction over here. It's the total number of documents in the collection divided by the total number of documents that mention this word W, okay? So this is a function that takes a word in a document, and this is a function that takes just a word and the whole collection of documents. The TF-IDF is just these two quantities multiplied together. And what does this do for us? Like, why is this interesting? We're just multiplying together counts of words and documents. Well, what I like to do is work out examples whenever I have something like this in front of me and I'm trying to understand it. So let's pretend that a particular document D is a review of a very hoppy beer. And we're going to compare the TF-IDF on D in this particular document of two words. We're going to start with the word hoppy, okay? So let's take a look at what the IDF for Hoppy could be, let's say our total number of documents is about 1,000. We've got 1,000 beer reviews, and 250 of them have the word Hoppy in them. So maybe only 250 out of those 1,000 reviews review Hoppy beers, which now that I'm saying that sounds super unrealistic, but please just go with it. So this is about 4, okay? And then because D is a review of a very hoppy beer, it uses the word hoppy about 10 times, okay? So the TF-IDF for hoppy in this document is going to be 40. So that should mean that maybe hoppy is a good tag for this review, right? Because we want something to pick out words that are important and interesting. And we just worked out a TF-IDF for a word that maybe should be a good tag, hoppy, right? Let's try a word that would be a very stupid tag. See what happens. Let's try the word the. I think everybody can agree that you shouldn't tag anything with the word the because it's a pretty useless and uninformative word for tagging a beer review because it shows up in almost all of the reviews, so it's not important. That's what this inverse document frequency is getting at. So let's work out the. The IDF for the is going to be almost 1 because it's going to show up in almost every review, right? And then the term frequency could be pretty high, right? In our document D, that's a review of a very hoppy beer because we say the pretty often. But if you take the TF-IDF, it's going to stay at the raw word count. It's not going to be increased because we know that the word the just isn't very informative. So if we compare these scores, the word hoppy wins because the inverse document frequency is helping us figure out, oh, this is an important word because it doesn't occur in all the documents. It only occurs in the reviews of super hoppy beers. If we did this for every word in the reviews and then picked out the top words by TF-IDF scores, maybe we would have some pretty okay tags. So it's a resolution here. We Google TF-IDF, find a gem to do that. And then as initial tags, we just take the top 10 words per review sorted by their TF-IDF score. And that's the end of our story. Except no, don't do this. I lied to you a little bit about exactly how TF-IDF is defined. And there's way better techniques out there that can rank things by how important their words are. But TF-IDF, or generalizations of what we just talked about, are used by real search engines like Apache Solar and Google and keyword ranking for searching documents and giving tags to documents. So again, this is a simplified example of a system of algorithms that actually exist and are used successfully in the real world. Okay. There's a lot of things I didn't tell you. Most things, in fact. If there's a thing, I probably didn't tell you it. I didn't tell you how to design algorithms. The whole, shtick of this talk was saying what an algorithm is, when you might want to use one, and how you would go about finding and using it. Design is something that you would learn in a course about algorithms, generally coupled with these modeling skills that I've been talking about. Didn't talk about how to assess the performance of algorithms. Algorithms differ wildly in terms of how fast they are. That's why sometimes you need to move outside of the CRUD paradigm when you have very large data. You need to restrict your problem and do something fancier to get acceptable performance. Otherwise, just keep using your database. I also did not tell you what big O notation is. Sometimes it's important for coding interviews. Also, sometimes it's actually important for working on large systems. But you can find that out for yourself and hopefully with more context given this talk. Now I want to close out by giving some resource recommendations. And I'd like to note that none of the things that have these resources have paid me to do anything. The only people who pay me are the Pacific Institute of Mathematical Sciences. And even though you have to pay for some of this stuff, I just think it's the best resources out there for learning about algorithms on your own. There's going to be two general categories of resources. One is academic, and that means it's more traditional computer science curriculum kinds of resources. It puts ideas first. The other is industrial. It puts code first. These types of resources complement each other, and they are both very good for self-study. It's best to use a mixture of academic and industrial resources if you're a working developer. First thing that I'm going to recommend is a data science MOOC out of UC Berkeley. It's called Data 8, and it is an excellent foundational introduction to statistical models. Not only will it teach you the basics of statistics and statistical modeling, it will also teach you the basics of Python while you're at it. It is a great course. I highly recommend it. It is completely free online. But it's very much ideas first, right? From the industrial end, there is another course from Fast AI called Course 18, Intro to Machine Learning for Coders. This takes a code-first approach to machine learning systems and shows you how to implement popular and powerful models and gives you the intuition for why they work. Also a great course, completely different orientation, right? Data 8 starts with ideas, Fast.ai starts with the source code. On the combinatorial end, Google Steven Sciena. He has many free lecture videos on YouTube and a algorithms textbook that is written in a way that is actually entertaining and story-based and surprisingly easy to read. And then also on the combinatorial side, from a more code-first perspective, there is an excellent book from the Pragmatic Programmer Press called A Common Sense Guide to Data Structures and Algorithms. And they're actually in the middle of putting out a second edition right now. And again, that starts with the code. Sciena's book starts with the ideas. So these four resources are an excellent way to get started in self-study of algorithms in both the combinatorial and statistical sides of the discipline. So this is actually the end of the talk. Thank you very much for your time and attention. And if you have any questions at all, I will be happy to take them now, hopefully with some kind of facilitation or something, because I am not great at taking questions over Zoom yet. Thank you.
So if anyone has a question, I'd say go ahead and raise your hand. I'll try to keep track on my end. Or you can put it in the chat and we can go in that order. Even if you just want to put your name in the chat, that's fine.
I have a question. So our cohort is currently in week 5 of our boot camp. At what point do you think, as we're steaming through all of this stuff that we're learning, are we going to butt heads with algorithms like you're talking about and be faced with those, like the conflicts you were talking about in those stories, and needing to approach it from those angles and remember the inputs and how that all works?
So where are you at in week 5? Can you say like roughly what the curriculum has covered there?
We have covered HTML, CSS, JavaScript, and React. We've moved into Ruby and are in Ruby on Rails with Postgres right now.
Okay, so I would say that at this point in your curriculum, you're going to be pretty comfortably operating inside of the CRUD paradigm. So you're probably, the exercises that you're doing, you're probably going to be fine just farming out the algorithmic work to the database. The database is basically, it handles algorithmic problems for you as long as you can phrase those problems as SQL queries. So I would say that you're going to start needing to deal with this material towards the end of your time at Learn, where you're talking to clients, you're in an internship, and sometimes customers are going to come to you and they're going to ask you to, basically they're going to ask you to do something that's not a CRUD thing. And then that's where you start dealing with this process. That's where you start thinking, oh, okay, my database doesn't cover this ask, doesn't cover this request. What can I do? Does that help somewhat? Because generally inside of these curricula, you're being taught to master like CRUD based development first, because realistically most problems are CRUD problems. Databases are fantastically successful for a good reason. um, you can choose to seek out more algorithmic problems in your career, or you can choose to become a specialist in database driven solutions at websites. It's really up to you, but it's good to know that these other types of techniques are out there.
No, that's really helpful. Thank you.
Okay. And then
Marco, we've got one in the chat from Austin.
Yeah, so first question, why not combine algorithms? Results of the first algorithm could help us further model difficult rules for inputs and outputs. Hilariously, that is a thing that my research is actually about. My research is about a technique called boosting, which it's exactly this. It is a meta-algorithmic technique for taking a bunch of algorithms, assessing how they're doing on a problem, and then turning them into a committee that does better on the problem than any individual algorithm. It's super cool and fun. If you want to read up about that, it is called boosting. It's generally considered a machine learning technique, and it's seen enormous success in data mining and knowledge discovery stuff. What is the deal with calling statistical algorithms AI? I don't know. I refuse to take a side in the call it AI versus call it statistics debate. I think that true human equivalent algorithms is a great long-term open-ended research agenda, but that is not what we have right now. But if we want to call those things artificial intelligence and have it refer to, very, very limited small slices of human intelligence, such as labeling pictures as to whether they have a cat in them or not, perhaps the most important task of artificial intelligence image algorithms, fine. I'm not really here to debate labels about the fields. I'm here to study what's going on and study what the algorithms can do, and cut them up, like cut up the space for you into basically statistical and combinatorial types.
A quick question for you, Marco. So when you're dealing with databases that have data that are ever changing, some static, some changes, minute to minute, some changes day to day. For instance, if you're talking about behavior, or if you're looking at human behavior, birthdays don't change, but how I'm feeling does. When you're working with algorithms, and especially when you're talking about boosting, like how would you approach working with or being able to do any kind of like, I want to say predictive modeling, or being able to have these algorithms change with the data that's coming in? Like what kinds of techniques, traits, books, or kinds of things can you recommend to someone that's working with dynamic data?
Absolutely, yes. That is a major area of research, and what you want to Google for and look for is something called online algorithms, online machine learning, where the word online refers to this setup where it's not just a static problem. You don't just have a big pile of data and then you learn a model from that data and do predictions with it. No, data keeps coming at you, and you have to update your model and give out predictions every now and then. So look up, I'll just drop into the chat, to the whole chat. So, so for changing data, you want to Google streaming algorithms and online learning.
Awesome. And how often update your models and your I guess how often would you, or how much data would you need per se to be able to say, okay, we're going to go with this model and then we're going to change it?
That depends completely on the application.
Sure.
So for most situations, you're going to have tools that assess the performance of your models, and you're just going to need to listen to those tools. Most statistical algorithms also come with a sort of a benchmarking practice where you analyze your errors, and they also tell you how confident they are in those errors. So generally, as part of the algorithm, there's also a method for assessing how well the algorithm is doing.
Cool. Thank you.
Anyone else out there with questions for Marco? Okay, looks like not. Okay. Well, Marco, we really appreciate you spending some time with us today. This is not my field of expertise, but I was fascinated. So I hope everyone else was as well. But thank you so much for taking the time to come and talk with us today. It is greatly appreciated. Little round of applause from everybody. Thank you so much, Marco. And we did go ahead and record. So yeah, we'll make it available to you guys for later review. Okay. All right. Thank you, Marco.
Thank you.